Welcome to The Explainer. Today, we're taking a deep dive, literally, to answer a huge question. How do the layers of our planet actually work?
We're going to peel back the layers of our planet to get a handle on the incredible forces deep inside that shape, well, everything we see on the surface.
So let's dive into this hidden world. But hang on a second. How do we even know what's down there? I mean, we've never drilled past the crust. The secret is actually earthquakes. Yeah, scientists use the seismic waves they create, kind of like giving the planet a giant ultrasound, to map out these completely distinct layers. And what they've found is this place of unimaginable extremes, way more dynamic than the solid ground we're all used to.
Our journey starts right here, at the surface. You see, the Earth's crust isn't one single, solid piece. A much better way to think about it is like a cracked eggshell. It's a bunch of rigid, rocky plates that are always, very slowly, on the move.
This whole concept is called plate tectonics, and it's basically the master key to understanding our planet's geology. Just think about it for a second. This one theory explains gigantic mountain ranges, the violent power of earthquakes, and even how entire oceans are formed.
Now here's where it gets really interesting. Not all of this crust is created equal. We've got two very different types. The dense, dark basalt rock that makes up the ocean floors, and then the lighter granite that our continents are made of. And as you're about to see, that difference changes everything.
I know you look at these numbers, 2.7 versus 3.0 grams per cubic centimeter, and it might not seem like a big deal. But in geology, that tiny difference is a massive gap. This one little factor dictates exactly what happens when these colossal plates slam into each other.
Think of it like this: a dense rock sinking in water while a piece of wood just floats on top. When oceanic and continental plates meet, that denser oceanic plate always loses. It dives down into the Earth's interior. This process is called subduction, and it's where the real action happens, creating the biggest earthquakes in some of the most volcanically active places on the entire planet.
So what's actually powering all this movement? For that, we've got to go deeper, down below the crust and into the mantle, the vast, superheated engine that drives this whole planetary show. The key process happening down here is convection. The best way to picture it is a giant pot of thick, slow-boiling soup. Hotter material from the bottom rises up, spreads out, cools off, and then sinks back down again. The tectonic plates we live on are basically just floating on top of these huge currents, getting dragged along for the ride. Now, the speed is incredibly slow. We're talking 1 to 2 inches a year. That's about the same speed your fingernails grow. But you have to remember, you give that tiny bit of movement millions and millions of years, and it suddenly becomes powerful enough to literally move continents, tear open new oceans, and build mountain ranges that tower over the clouds.
Okay, let's keep going deeper. We're now reaching the planet's fiery heart, the core. And this is where the conditions just get truly extreme. The temperatures and pressures here are almost impossible to wrap your head around.
You might picture the core as just one big, solid ball of metal, but surprisingly, it's actually split into two completely distinct parts, and the difference between them is absolutely vital for all life on the surface.
Right at the very center, we have the inner core, a super dense, solid ball of iron. But surrounding that is the liquid outer core, which is basically a swirling ocean of molten iron and nickel. It's the interaction between this solid sphere and the liquid ocean around it that generates one of Earth's most important, and yet totally invisible, features. The inner core is unbelievably hot. We're talking around 6,000 Kelvin. To put that in perspective, that's as hot as the surface of the sun. All that immense heat flowing out from this solid ball is what stirs up the liquid outer core, driving these powerful convection currents within it.
So why should we care about a churning ball of metal thousands of kilometers down? Because all of that motion turns our planet into a giant magnet, creating an invisible shield that is absolutely essential for life to exist.
This process has a name. It's called the geodynamo. As that conductive molten iron swirls around in the outer core, it generates massive electrical currents. And those currents, in turn, produce Earth's magnetic field, this protective bubble that stretches tens of thousands of kilometers out into space.
And this field, it's our planet's first line of defense. It deflects something called the solar wind, a constant blast of charged particles from the sun that would otherwise just strip away our atmosphere and our protective ozone layer. Without it, harmful radiation would bombard the surface, and life as we know it would be impossible.
Okay,
So let's zoom back out for a second and connect all these pieces, from the very center of the Earth all the way up to the surface we live on.
It all starts with the incredible heat radiating out from that solid iron inner core. That's the ultimate source of our planet's geologic energy.
That heat gets the liquid metal in the outer core churning, which fires up the geodynamo and creates a protective magnetic shield. And that same deep heat just keeps rising, driving those slow-motion convection currents in the mantle. And it's those currents that drag the tectonic plates of the crust all across the planet's surface, creating mountains, oceans, and earthquakes along the way.
So the big takeaway here is this: the ground beneath our feet is anything but static. It is the surface of an incredibly complex, active, and ever-changing world. Every single layer is connected in this massive chain reaction of heat and motion that has shaped our planet for billions of years. And as it all continues to churn, it leaves us with a pretty fascinating question. What will our world even look like millions of years from now?